All right. Welcome, everybody, back to the monthly Ceph Tech Talks event here on our Blue Jeans video conferencing system. For those of you that aren't familiar with the Ceph Tech Talks, these are basically a 1-hour deep dive on a technical level of something at least tangentially related to Ceph. Thankfully, we've had some pretty core discussions thus far. We've had, Rados and the block device and the gateway, and we looked at the Calamari Romana during that split. We've talked about some placement groups, and we had a nice examination of CephFS in July. This month, it's going to be Mark Nelson, who's our lead performance engineer, who will be looking at the performance tuning world in Ceph and using some recent findings to help share kind of how we arrived at some of our recent decisions. In the future, if other people would like to give a Ceph Tech Talk, anyone from the community is welcome to do so, as long as it is relatively technical and Ceph related. We're looking at potentially in September, so next month, doing a discussion of someone who's been working on Ceph integrations. So looking at kind of the start to finish on how to do a Ceph integration with some piece of custom software. But if anyone has any other ideas, feel free to contact me. Otherwise, afterwards, you can find the videos here for replays or linking elsewhere via the Ceph-Tech-Talks page on Ceph.com. So without any other preamble, I think we can get started here. Mark, you wanna lay it on us?
Sure. So I will start out by saying that Patrick reminded me yesterday that I was scheduled to give this talk, and I scrambled to put slides together. So I don't know that we'll take up the full hour, but we'll go for as long as we can, and maybe we'll have time at the end for folks to ask questions if they would like to. So basically, what I want to talk about today is just kind of a general overview of how we do a lot of testing at Red Hat, and kind of give an example of some of the recent things that we've done. So at Red Hat, and this is mostly kind of carryover from when we were Inktank, we use two kind of major pieces of software for doing a lot of the performance testing work. Those are Teuthology and CBT. There's actually also various software pieces that our consultants have written that they use as well, although I don't actually know too much about them, so I'm not going to talk about those today. But in terms of what we've been doing kind of in engineering, Teuthology is our kind of nightly functional test framework that is used to run almost all of our nightly regression tests and also some performance tests as well. We actually recently went in and kind of analyzed what Teuthology was spending most of its time every night doing, and a lot of it is things like running Rados tests with thrashing happening in the background, so marking OSDs down and increasing PG counts for different pools, and more or less just really trying to stress the cluster while doing various Rados commands or other things at the same time. So that's kind of Teuthology. CBT was written a couple of years ago as kind of a lighter weight performance benchmarking oriented tool than Teuthology. Teuthology is really kind of big and does a lot of things like more or less deploying nodes and setting up software and doing a lot of that kind of infrastructure related thing. CBT doesn't do any of that. CBT basically assumes that you already have a number of nodes set up that have Ceph on them already, and then it will build a Ceph cluster optionally for you and run tests on those nodes. It doesn't do any kind of like software installation, but it will at least automate the Ceph portion of the setup and running the tests. We use CBT quite a bit in the engineering group. It's also used by the reference architecture team inside Red Hat for like testing on partner lab equipment, and then also by our QE group for doing like nightly performance regression tests against Red Hat Ceph storage. There's a lot of different tests that we use CBT for. It's everything from looking at cache tiering performance under different scenarios to actually benchmarking some of the functional tests that are run in Teuthology under different scenarios. So we use it for quite a few different things. It's an open source tool. It's uses YAML for the configuration files, and it can also run a lot of monitoring in the background. So Collectl is a tool that's used quite a bit for looking at like node statistics, and CBT will run that for every single test. It also can use Valgrind to profile different daemons, and also run things like block trace in the background, or other kind of monitoring type tools like perf for node profiling. Let's see. So in terms of hardware at Inktank, or rather at Red Hat, for a long time we didn't have any really good high performance gear. I had a box basically sitting in my basement that was kind of designated the Inktank Performance Lab back in the day, but it was more or less just a single 4U Supermicro node that I swapped configurations around, left and right, trying to determine what different things made Ceph perform well and what kinds of different hardware configurations Ceph did not perform well in. Well, just recently, in the last couple of months, Intel very generously donated 8 really high performance nodes to the Ceph community, which Red Hat is hosting in the Ceph Community Lab. And those nodes have 10 spinning disks, although those aren't very interesting necessarily at this point from a performance perspective, because there's a lot of other nodes out there that have similar configurations. But each one of these nodes has 4 800 gigabyte NVMe SSDs in it, which is fantastic. There's a lot of backend throughput and IOPS that we can actually now finally test Ceph on a regular basis, trying to determine how to improve performance on this kind of a setup. These nodes have fairly reasonably fast processors, and each one also has a dual 40 gigabit QSFP plus Ethernet adapter in it. And luckily for us, Mellanox actually recently provided us with a 12-port 40 gigabit switch. So we were able to hook all of these nodes up together and actually get really pretty good performance with them. They also have 64 gigs of DDR4 memory, which is very nice. Pretty reasonable actually for how fast these things are and how much disk they have. So we just got those nodes set up right before the first Ceph hackathon took place earlier this month out in Portland. And we were looking for a kind of an initial test case. We had done some kind of real initial performance tests on it using FIO and Rados Bench through CBT, but we didn't have any kind of really good example for this thing. So when we went up to the hackathon, we were kind of looking to see, well, what could we do with these at the hackathon to kind of showcase their usefulness and also provide the community with some interesting results. And at the hackathon, Jian Zhang from Intel presented some very interesting tests that he had done looking at tcmalloc and jemalloc. And this was based on some work that SanDisk had done earlier this year, also looking at both of these different memory allocators. And actually, they had found a bug in tcmalloc where you couldn't change the thread cache settings in the version of tcmalloc that was distributed with almost all distributions that are out there right now. Ubuntu, RHEL, CentOS, I think Debian as well. And this was a big deal. They found that the default thread cache values in tcmalloc actually were causing Ceph to not perform well for small I/O. And Intel's results that they showed at the hackathon reiterated those findings. And in fact, they went into it in a little bit more detail. So when I saw that Intel had posted these numbers, I became really interested and thought, well, hey, we're here at the hackathon. we've got these nodes, we're looking for a test case for them. Maybe we can go and use CBT to try to replicate the findings that both SanDisk and Intel had seen. So basically, within a couple hours, we sat down at the hackathon and created a CBT configuration that let us try to do that. So in CBT, you define in the YAML file basically the cluster that you want set up and the tests that you want to run. And I haven't included all of the different things that you put in the YAML configuration file here. You can look at kind of the examples directory in GitHub or ask me or ask on the mailing list how to do that. But one thing I did want to point out here is that when you're setting up the cluster, you can specify the cephosd command to run. And in this case, I'm actually using a precompiled or a compiled version of Ceph that was from Git. And as part of the cephosd command, I'm actually setting an environment variable here, in this case to change the tcmalloc thread cache settings. You can also potentially use LD preload here to actually set the memory allocator to use for the cephosd process. I didn't actually do that here. I actually recompiled Ceph to just use the different memory allocator for each run, but potentially you could actually use LD preload. Some people might consider this a kind of a lack of input validation, which is very true on CBT's part, but it does let you kind of do useful things like this. So it's a little bit of a mixed bag. Hopefully no one would be doing anything really terrible with CBT in terms of passing malicious things in, but it is kind of nice to be able to change environment variables that you're passing into the processes. So in each case, for every single test that we ran or every single different memory allocator configuration that we tested, we rebuilt the cluster using CBT the exact same way. Every single cluster was configured using the exact same steps. And that's kind of one of the things that CBT buys you, is that if you're going to be doing a lot of repeated testing, you can make sure that clusters are set up the same way. You can actually tell CBT to rebuild the cluster before every single test if you want that to happen as well, although that takes a long time. There's actually some pull requests right now that I need to look at from Ben England to try to speed up cluster creation. He has gone through and looked at how to parallelize as much of it as possible. And that does help, but still, that's a big time sink in terms of building the cluster every single time. So usually you kind of build it once, maybe for a set of tests, and maybe you rebuild it again for a separate set of tests that you're comparing against the first, or at least that's how I typically do it. So when we ran through these tests for the hackathon on the performance cluster, we ran through a whole ton of different tests. Random writes, random reads, sequential writes, sequential read, mixed I/O tests at various different sizes, 4 megabytes, 128 kilobytes, 4 kilobytes, just a kind of a whole battery of tests. I have not included all of those because it'd take hours to go through all of them. But the most important or most interesting ones were the small I/O tests, at least regarding the different memory allocators that we looked at. A couple of things that we found out from this testing is that Ceph is really hard on memory allocators. There's probably a lot of different opportunities for tuning here, and there's a couple of different folks that are looking into that. There are huge performance gains and latency drops that are possible. In the next slide, you'll actually see for 4K writes how big of a performance gain we saw, but definitely there's a lot of potential here. What we also saw in these tests is that small I/O is really still CPU limited in all of these tests, even in the fastest configurations. So that's another thing that we'll need to spend more time looking at, are ways to try to reduce that overhead. And the final thing is in every single test, regardless of the I/O size or the I/O type, jemalloc used higher amounts of memory. In many cases, it provided higher performance, but it always used at least like 200 to 300 megabytes more RSS memory per OSD process. So that's a big deal. There's a lot of folks that are running large OSD configurations, nodes that have 30 or even 60 OSDs on them, and a 200 to 300 megabyte increase in RSS usage per OSD would push them over kind of the expectations that they had when they built those clusters. So we need to think about how we can try to gain some of the performance that we're seeing in jemalloc without necessarily increasing memory usage that much. Those are kind of the goals going forward. So let's take a look here. In terms of IOPS for 4K random writes, if we look at tcmalloc 2.1, which is the default that's basically distributed with most distributions that are out there right now, with a default 32 megabyte thread cache size, which is actually the only size that you can use with tcmalloc 2.1. We're seeing pretty anemic IOPS. It's 20,000 write IOPS. Considering how fast these SSDs are, that's a small fraction of what they can do. When we switch to the newer version of tcmalloc with 128 megabytes of thread cache, it starts out really good. We're about 4 times faster, but it degrades over time. We see it kind of trailing off and ending up somewhere around maybe 64,000 IOPS, which is still much better than it is with the current default tcmalloc, but it's kind of concerning. We don't know with very, very long running tests how much it may degrade. It looks like it's maybe leveling off, but that is still pretty concerning. jemalloc, on the other hand, is pretty consistently about 4 to 4.1 times faster than tcmalloc 2.1. It's a big increase, and it's looking really consistent and nice. We're still CPU limited. When we look later on at the CPU results, you'll see that. But potentially, if we can reduce CPU usage, or if these nodes had even faster CPUs in them, we may be able to even get more out of the SSDs than we're seeing here. So in addition to higher IOPS, we also saw a really nice decrease in typical latency. FIO, which is the test that CBT ran in this case, provides a latency distribution for the tests that it runs. And so we were able to look at every single client process. In this case, we actually had 16 FIO clients, and I want to say maybe 512 concurrent IOs going at once. And we were able to see a decrease in latency as reported by FIO from like around a typical 50 millisecond latency for these ops down to around 10. So, really, really good improvement. Still not as low as we'd like to see. Again, this is CPU limited, so that's where we think, we're just backing up. We're processing as many IOs as possible, and things are waiting. So when we look at read IOPS, which are much less CPU limited, we actually saw that around 98% of the 4K random read IOs were 2 milliseconds or less. So we're at least for reads getting really close to that 1 millisecond mark. We're not quite there yet, but really close. So that's really good. It means that I think we'll be able to get there for writes, as we continue to find ways to improve CPU utilization and just kind of generally optimize the code. So here's where we're seeing that we're CPU limited. Basically, in all configurations, CPU overhead was not quite at 40 cores, which is technically it's 20 cores with hyperthreading, but we're up around like 34 to maybe 35. Now, FIO was running on these nodes at the same time as the OSDs. We unfortunately, didn't have time to get clients set up on the 40 gig network. So we were actually running FIO on the same nodes as the OSDs. And FIO itself was using about 5 cores of CPU just for the client IO. So we're pretty close here to maxing everything out. it's kind of weird in the 64 megabyte thread cache case with tcmalloc that we actually saw it maybe kind of go a little bit down, more like 30 cores being used. I don't know exactly why. Maybe there was some other reason for that, but we're still really quite up there using almost everything. And in the other cases, we're definitely pretty much pegged. So the downside here to jemalloc is that it uses more memory. It's really fast and it looked really consistent, but this is what you pay for to get that kind of performance. You see probably around like 300 megabytes more RSS. tcmalloc, when you increase the thread cache, also uses more memory, but it actually wasn't as high as I expected. It may be that tcmalloc, the new version of tcmalloc, and increasing the thread cache is good enough that it's not quite as high memory usage as jemalloc, and it does get you a lot of performance, although that trend that we saw where over time the performance was decreasing is troubling. So whether or not that levels out is probably going to be the determination of whether or not tcmalloc is really something that's going to be good in high performance configurations going forward, or whether or not jemalloc is just kind of the definite way to go. In terms of jemalloc, the really big question is not how much memory it uses in kind of the typical scenario like this, it's what happens during recovery. And so that's actually what we did after looking at the performance in these different tests. We said, well, okay, it's not enough to know that jemalloc is doing well with this kind of memory usage under typical scenarios. We need to know what's happening when an OSD is recovered, because that's when the OSD tends to use the most memory. And luckily, for about a year or year and a half now, we've had a capability in CBT to perform recovery tests during benchmarks. And so basically in CBT, in the cluster section, the Ceph cluster section, there's a state machine that will run through and try to basically go through a number of steps to have a cluster mark various OSDs down, wait until the cluster is healthy, and then mark them back up, and wait until the cluster is healthy again. And it's a really simple configuration change. Basically, in the cluster section of the CBT configuration file, you specify that you want a recovery test, you specify the OSDs that you want marked down and marked back up, and then there's a couple of other parameters you can adjust. We didn't adjust those in this case. Basically, there's a wait period at the beginning of the test to wait before the OSDs get marked down, and then there's a wait period at the end of the test for how long you want the benchmark to continue to run until the overall test completes. You can also specify that you want the recovery test to continuously mark OSDs down and back up throughout the duration of the benchmark. So if you specified that you want to run a test for 1 hour, it will continuously go through and run the recovery test, basically going through the entire state machine over and over and over again until the benchmark completes, upon which time then the recovery test basically just finishes up and exits out. So we basically went through and ran this for tcmalloc and jemalloc with 4K random writes again to see what happened. And what we saw actually is that in all configurations with all memory allocators, there is a big spike in RSS memory usage when recovery happens, when these OSDs are marked back up and in, and the cluster is dealing with that before it becomes healthy again. With tcmalloc in a 32 megabyte thread cache configuration, and these numbers are actually very similar for tcmalloc 2.1. We didn't run through those tests here, but basically 2.1 and 2.4 looked very similar in our previous testing. So we just looked at 2.4 here. We see that there's a memory spike, but it's not quite as big as it is either with 128 megs of thread cache or with jemalloc. jemalloc, again, was by far the biggest spike. And we're seeing here that actually jemalloc is using somewhere around maybe 500 megabytes more RSS memory than the 32 megabyte thread cache configuration with tcmalloc, and it's using somewhere around maybe 200 to 250 megabytes more RSS memory than tcmalloc with 128 megabyte thread cache configuration. So unfortunately, we're seeing a pretty big spike. There's a lot of memory usage, a lot more memory usage in recovery with jemalloc, especially compared to what we see with the current Ceph configuration, or at least common configurations with Ceph right now with tcmalloc 2.1. Now, having said that, if you look at how deep these graphs go in terms of time, with jemalloc, recovery happened over twice as fast as the current kind of default configuration. It was still faster than tcmalloc with 128 megabytes of thread cache, though not quite, not as significantly faster. But that's a good gain. That's an impressive gain, right? I mean, if recovery happens that much faster, that means that your cluster is healthy more often, and a larger percentage of the time. So that's really nice. That's a really big benefit. So unfortunately, there's a trade-off here: more memory or better recovery and better performance. So our work going forward now is to figure out, can we make jemalloc or tcmalloc better? Can we reduce jemalloc's memory usage, or can we increase tcmalloc's performance without increasing memory usage? So far, we've started looking at jemalloc. We've upgraded to 4.0, which just came out about a week ago, and that seems like maybe it's helping slightly, but it didn't do much in our tests. It was, if there is an effect, it's really small. On the mailing list, there's been some discussion. Other folks have looked at this and have seen a little bit more of an effect with jemalloc, the new version of jemalloc, maybe on the order of, if I remember correctly, maybe like 7 or 8% better memory, lower memory usage. So it's possible that maybe there is something there, but we didn't see much. We tried changing a lot of different jemalloc parameters. They let you pass in an environment variable to set the malloc conf, and you can change different settings that way. Everything we tried had almost no effect. It's quite possible that we were doing something wrong. So we need to figure out if we're not doing this correctly, or if something's happening. You can tell jemalloc to print out statistics on exit, and that will tell you what those settings are. So we tried to go that route. Unfortunately, when we issued a sig term to the OSD, it caused the OSD to segfault. Since we've done that, we've had some feedback that specifically we need to probably run the OSD in the foreground rather than daemon mode. There's also some documentation in the jemalloc man page that printing statistics can cause deadlocks if there are threads that are trying to allocate memory at the same time. So that could be related. We both tried to print statistics through the malloc conf setting that jemalloc provides at exit, and then we also tried to instrument statistics printing directly into the Ceph OSD shutdown process, or shutdown function. Neither worked. They're both still causing segfaults. And it's quite possible that maybe just using jemalloc in general is causing segfaults when sigterm is sent. I don't know yet. So there's still a lot of work there that needs to be done to try to figure out exactly what's going on here and get good statistics out of jemalloc. It does provide a lot of really useful looking statistics, and also profiling data that's compatible with gperf tools. So this is really nice. Potentially there's a lot of data that we can get out of this to find out more about what's going on in terms of memory allocations, and then also whether or not we're modifying the settings correctly. So beyond just trying to tweak memory allocators and play with what things are being used for Ceph, in parallel, there's an effort going on right now to try to improve Ceph's behavior. Ceph is really, really hard on memory allocators. I think these results pretty much show that, and we've kind of known that for a while. But the improvement in performance that we're seeing here kind of makes it a little bit more crystal clear. So various folks are working on this. Pyotr Dalek from Fujitsu specifically is one person that's been doing a lot of work in this area, and potentially some of the patches that he's already submitted are going to improve performance and maybe even affect memory usage. And there's probably a lot more that we can do beyond that as well. We've got a lot of investigation to do, a lot of hard work to do. Some of the other folks on the performance side at Red Hat recommended actually modifying or implementing our own memory allocators in Ceph, which would probably be a fairly major undertaking, but potentially might be something to think about. And we also need to look at some of these other new things that are being committed to Ceph as well, like async messenger, where the amount of threads that Ceph creates are actually far lower. It uses a thread pool with polling. And there are other things that are also being implemented, like XIO Messenger and various other things that may affect all of this. So there's a ton of work that's happening, and there's a ton of testing that needs to happen, and a lot of different people are looking at this. Actually, every week we have a weekly performance meeting where folks get together and kind of discuss all of these different things that we're looking at, and people present their results. So if you're interested, certainly feel free to stop by. I post every week the meeting invitation. It's Wednesday mornings at 8 a.m. Pacific time. So feel free to stop by if you're interested and if you'd like to participate. Otherwise, there'll certainly be more of these kinds of things, more presentations and newer versions of Ceph. Hopefully, we will be able to integrate all of this and really see dramatic performance increases, especially for small I/O. So that's it. That's all I've got. Well, I think the background didn't show up here, right? It's kind of a blue color, but yes, that's all I've got. So feel free to ask questions. I have no idea how long that took, but I imagine we probably have time. So that's it.
Plenty of time. Yep. Looks like Joe asked a question a little while ago about why not do in-application memory management.
Yes. So probably because no one's had time. I'm guessing the right answer. I think that probably talking to Sage about that would be the way to go and see what his thoughts are. He knows the code far better than I do. Actually, if Piotr is on, he mentioned on the mailing list that he had actually, I think, done some initial investigation and was seeing just stuff all over the place that needed work. But Piotr, are you around? Do you have microphone access?
Yeah, I do. Can you hear me?
Yes.
Oh, great. So regarding the memory usage and memory behavior of the Ceph, what has puzzled me in the past was at first the memory usage of the radius benchmark itself, and then I realized that there is a lot of memory shuffling going back and forth. Quickly, I have identified that there is a similar behavior in the entire Ceph code base, including those buffer lists. So this is a lot of work that needs to be actually done on this matter. If we actually want to have a lot better Ceph performance at all, we need to have this performance behavior simply fixed. We might replace the tcmalloc with jemalloc, but this will be a short-term solution that will work and will increase memory usage for most users, but it won't fix the root issue. So from my side, I'm going to work on this any further. So there will be a lot less memory allocations and deallocations going on.
Yeah, I agree with you, Piotr. I think what we're seeing here, right, is that jemalloc is sort of a band-aid, right? It's doing much better, but it's pretty clear that Ceph is really stressing the allocators. So there's a lot of work that we need to do to stop that from happening. And who knows? Maybe once we do that, jemalloc and tcmalloc will both start looking more similar in terms of their behavior. But at least for right now, kind of as the short-term band-aid fix, if you can handle the increased memory usage, you can definitely get much better performance out of jemalloc.
That's true.
So let's see. We got a whole bunch of stuff in here now.
Yeah. In the meantime, people that want to ask questions, some are hitting via the Blue Jeans chat here, which is fine. If you want to unmute your microphone, you can ask a voice question, or you could use the Ceph IRC channel. So any of those are acceptable. Looks like Brian has the next question asking, have you done any performance testing of NewStore with HDDs compared to FileStore with SSDs journals?
Yes, we have. So I don't remember all of the results off the top of my head, but what we have been seeing with NewStore is that it's faster in almost all cases except for RBD style object overwrites. So this is actually object overwrites in the general case, but RBD is where you see it happen a lot. If you're doing like say a 512K write into a 4 megabyte object, NewStore has been slower than FileStore in those cases. Part of it is due to how RocksDB does its write-ahead logging. Basically, there's a lot of overhead due to it recreating a log or creating a new log every so often. I don't remember what the default values are, but it periodically creates new log files and then gets rid of the old ones. Sage actually in the last couple of weeks has implemented kind of a hacky change into RocksDB that allowed it to kind of recreate the log file in place. And that, I think he said, yielded about a 15 or 20% performance improvement when he did that. But he needs to kind of rework that and present a formal pull request over to the RocksDB guys before that will make it in. And we'll need to do a lot more testing on NewStore after that happens. Another alternative might be to take objects in NewStore and break them into chunks. So maybe like do 512K or 1 megabyte chunks so that portions of the object don't actually need to be rewritten if you're doing a partial overwrite. And that might help too. We'll just have to kind of see where we end up after the RocksDB changes and whether or not we want to go through all the work of implementing like object chunking. So that's kind of where we've been at with NewStore. I think a lot of work recently has just been going into getting all of the underlying code necessary for NewStore into Ceph so that NewStore can be merged in. Actually, there's open pull requests for that right now, so it's all happening kind of as we speak.
Awesome. Looks like the next question here was from KP. What kinds of performance testing do you do with cache tiering? Same set of tools, or any background you can share on your performance testing efforts on that front?
Yes, so we do testing of cache tiering, and CBT can actually go through and take a set of OSDs that you have defined in your ceph.conf file and designate those as a cache tier. So what it will do is basically modify all the crush rules and create a parallel hierarchy for the cache tier, and then go through and kind of do all of the annoying commands that you have to run to create that cache tier automatically, and let you specify that should be a cache for some other pool. So actually in CBT, you specify profiles. You say that you have, say like a base pool profile and a cache tier profile, and then it uses those profiles to actually make pools during the benchmarks. And if you've specified it in kind of the expected way, then it will go through and automatically create the cache tier in CBT for the base pool that's being used for the benchmark. So some of the testing that we've done on that front has been focused on specifically on promotion behavior into the cache tier. What we've seen is that it's really, really easy to get to a point where there are excessive promotions, and that really drags performance down. The big reason for that is, say that you're using RBD with a cache tier and you have a 4K read miss. Well, that 4K read miss means that you've got a 4 megabyte, or at least by default, a 4 megabyte RBD object that gets promoted into the cache tier. Now, assuming that you have default 3x replication and that you're doing SSDs and you've got your journals on the SSDs as well as the data, that means that 4 megabyte object actually turns into a 24 megabyte write. So a 4K read cache miss is actually promoting 24 megabytes of writes into the SSD cache tier. That's really intense. It's really, really easy to overload the cache tier with excessive writes. Some of the testing that we did initially was basically just to pseudo-randomly reject 99% of the promotions. Say, we're going to just limit the promotion rate, to be very, very low, and really, really hot objects will eventually make it in, because even though only 1% of the promotions are making it through, they're so hot that that sooner or later they're going to make it into the cache tier anyway, and anything that's cold is basically going to get rejected. And we saw something like, I want to say around a 40 or 50x performance improvement when we did that. It was huge. It was actually enough that the cache tier started looking pretty good. It was not it was I don't remember. It went from being significantly slower than just using the base pool by itself to being maybe like, I want to say maybe like 40 or 50% faster than using the base pool. So that was really, really good. That was really important. In addition to that, write proxy support just got merged this week, if I remember right. That will hopefully help things quite a bit as well. Read proxy was merged maybe a couple months, like 6 months ago. There's a lot of work going on this front. There's probably a lot more work that needs to happen to look at the heuristics of when promotion happens, when eviction happens. Lots and lots of stuff on this front to look at.
Cool. Looks like the next question from Yuval is anybody looking at bringing more determinism by leveraging C groups, etc., using CPU affinity for OSD daemons, constraining RAM, etc., etc.?
Yes. So Kyle Bader in the reference architecture team at Red Hat has done some work on this, and also Ben England from the Red Hat performance team is planning on doing a lot more investigation into C groups specifically, and looking at both CPU affinity and probably memory affinity under different scenarios. I think there's been kind of a general interest in kind of like hyper-converged solutions, and so a couple of different people are interested in trying to figure out whether or not this can be accomplished without really significantly impacting the OSDs. I think it's going to be really important going forward to figure out, if you want like high IOPS, how to deal with the fact that we're basically maxing out the CPUs already for these kinds of workloads. So there's definitely going to be some contention in terms of resources when you want to do this. You'll have to be careful about how you design your nodes. Maybe you can only have a couple of SSDs if you also want VMs on those same nodes. There's probably a lot of kind of hardware reference architecture design work that will need to go into figuring out where the balancing points are. And certainly things like jemalloc and tcmalloc are going to fit into this, because we see such a huge shift in CPU usage when using different allocators. So definitely there's a lot of work there that needs to still happen, but people are looking at it.
Cool. All right, so the next question here looks like we're back to Brian, saying scrubbing can have its ionize values set to idle, but has there been any work on allowing you to set ionize values during recovery operations?
So I don't know is probably the right answer. I mean, there are things in Ceph itself for trying to shift kind of how much client I/O versus recovery happens. I don't know, specifically about ionize. I guess I don't know what's happened there. What I've seen when changing Ceph's options for kind of priority of recovery operations, that it basically changes as you have more client I/O, even past the saturation point on the cluster. So say you have 700 megabytes of client I/O under some kind of recovery priority settings that you've set. And now you increase the number of clients. So you've got more clients that are waiting to do I/O. When you do that, what seems to happen is that your client I/O performance might not change. You might see the same level of performance, but now all you've done is kind of made recovery take longer. It's kind of just made the situation worse in a way. What you optimally, in my mind, what you would think would happen is that you've said, okay, I want to devote under a recovery scenario, I want 30% of the traffic to happen to be recovery traffic, and I want 70% to be client I/O traffic. Kind of ideally, maybe that's what you want, or maybe you want different values. I don't know, but you would hope then that you would maintain that regardless of how much client traffic or how much client I/O you have. Even if you have more clients trying to do I/O, you'd hope that you'd keep those ratios, but it doesn't seem like that's what's happening right now. So, I think we need to kind of investigate that whole kind of area of the code and how it works to make this simpler and nicer for users. But that's just my take on this. Kind of what I've seen.
Right. Jane's asking if there's any performance hit when we write unaligned data, i.e. not in terms of 4K.
Good question. Are you talking specifically about RBD or objects? RBD. Okay. I don't know that I have actually tested unaligned RBD writes. I may have at one point, but if I did, I don't remember the results. So that's a very good question that I do not know the answer to. Something that we should probably work into our set of standard tests.
Nice. Andrew's saying that using the Swift API, they've been seeing some head requests on large MPU objects in Firefly take longer than 3+ minutes. Is there any optimization tips that you might recommend in order to bring this number down? Appears to be doing a head request on each part, which can take an extremely long time depending on the amount of parts.
So I think that if it's taking 3+ minutes, there's definitely something wrong, unless there's so much I/O that it really is taking that long, for the underlying hardware, but I suspect not. What I would suggest doing is looking at the different statistics, the different administrative socket statistics that you can get to performance counters, both for the OSDs and then for also the other daemons, and trying to figure out where in the pipeline you're stuck with outstanding operations. This is something probably that we should talk about with just offline out of this, because it would take too long to diagnose. But there's definitely, I think, something wrong going on there.
Evo's asking, regarding CBT, how hard is it to take the same test, YAML file, and point it to another set of nodes? Is it similar to Tautology's targets option?
So right now in the YAML file, you specify a cluster section that has the nodes kind of hard-coded, well, not hard-coded, but the nodes defined in the YAML file. Right now, currently, you'd need to make a copy of the YAML file and change those nodes to the new set of nodes. If there's also an option where you can target existing clusters. So if it's already running an existing cluster, you could basically just say use existing and then have it go off and target that cluster. There's some interesting work going on by Mirantis right now to try to kind of integrate like OpenStack provisioning tools into CBT. And honestly, I actually do not know that much about OpenStack at this point. I deployed a cluster like 3 years ago, and I'm horribly out of date. So I can't even begin to explain, what it is that it actually does at provisioning in those cases. But there is some work going on kind of to try to do that. In parallel, there's kind of a really simple enhancement to CBT that a couple of people have expressed interest in that would be really nice, that Tautology already does, which is to let you define multiple YAML files. So you wouldn't actually have to recreate the entire file. You just recreate maybe a separate node targets section, and then include that YAML or a different targets YAML for the cluster part of it. And that would be a really easy change. It'd be just basically letting the settings take in multiple YAML files and then adding those to the settings dict that gets created in Python. So that's kind of where it's at right now. We don't do any kind of like auto provisioning though, which maybe someday with like this OpenStack thing. So that's kind of where we're at.
Okay. Looks like the next question is from Nikhil. On cache tier for retesting, does reducing the order from 23 to either 20 or 19 when you create an RVD image help with performance?
So that's a really interesting question. And what we have seen is that there's kind of competing things going on. When you decrease the RVD default object size, there are some situations where that does lower performance because now you're not doing as big of reads or writes. You're not coalescing as much into one object when you're doing I/O. But in terms of the cache tier, it can actually help you because now you're reducing the promotion overhead. So depending on how quickly you can absorb writes into the cache tier, so whether or not you can really absorb extra I/O for larger objects versus the benefit that you get by having bigger objects, there's this kind of competition for what gives you the best performance. So kind of the answer is it probably depends on your cluster configuration and your network configuration and all of this kind of stuff. I think probably the best answer is you're just going to have to try it and see if it helps you with the stuff that you need. I suspect that for small IOs, for like 4K reads and writes, you would see a benefit by reducing the RBD object size, but for large IOs, you may actually see a decrease in performance. That would be my just kind of guess.
Okay. It looks like we've exhausted all of the existing questions. If anyone else have a question, throw it out there real quick. All right, it sounds like a whole lot of nothing. All right, well, thank you very much, Mark, for taking the time to give us the lowdown on Ceph performance. This video should be up before the end of the week here if people want to review it or share it to folks that missed out. So other than that, thanks everybody for coming. We'll see you again next month.
All right, thanks everyone.
Thanks, Mark.